Okay, and so the online lab is dealing with Hess law, which is exactly what we're going to be talking about today. And it's talking about heat of formation, heat of solution, and various types of calculations involving equations. And so that's what we're going to be really focused on today. So if you've started the lab, it might be a little bit confusing, but today should help clear it up. And if you haven't started the lab yet, then this will be a pretty good introduction to it. So first off, I sent out an announcement a little bit ago saying that homework 1 is available. It is, so feel free to jump on that. It's basically a little bit of a review material from solutions as well as the end of chapter 6, parts of chapter 7, and then chapter 11. And again, you'll have 7 days to complete it, so it's going to be due next Tuesday at midnight. And that'll be the same due date for the quiz. So I'll release the quiz on Tuesday morning next week, and then you'll have until midnight to finish the quiz. So any questions there? Excellent question, Rebecca. Oh yes, Haley, we definitely do. I'm not teaching lab this semester, so I'm not sure whether or not they're treating specific heat uh, as a constant. My assumption would be that specific heat has to be experimentally determined. So if it's only provided to you with 3 sig figs, then that's all the sig figs you're allowed. Because I think your mass, you'll have many more sig figs than that, as well as your temperature change. So probably specific heat will be the limiting one. I don't have access to the key for that lab since I'm not teaching it, so I can't double check it for sure. But I could go ahead and reach out to Professor Smith about that. So I'll make a note about that, and then I'll go ahead and post it. So C values, 3 sig fig, rotate. No problem. Okay, any other things going on with the quiz or just in general? So we're not going to have office hours tonight. So remember, late night office hours are on Mondays and Thursdays. And then after class, office hours are on Wednesdays and Thursdays. Okay, well, let's go ahead and jump in then. So where we left off is we were talking about enthalpy. And we had just gotten to the point where we were talking about heat flow as well as work. And one of the things that we had to really kind of come to terms with is that the direction of the work definitely can be a little bit confusing. So in other words, let's go ahead and just clarify. If we have, let's say we have a round bottom flask here, and we stretch a balloon over it. That's a balloon, believe it or not. And this is a demonstration that I do like to do, but don't have access to chemicals right here. And down here, if we have a chemical reaction occurring, so this particular chemical reaction might be A plus B gives us A, B gas. after the reaction is over, this balloon has inflated. And so what I'd like you to do is in the chat, I'd like you to tell me about was work done by the balloon or by the chemical reaction occurring inside the balloon, or was work done on the system, so the system being the chemical reaction. So go ahead and in chat. Very good. That's exactly what I want to see. So now the question is, if we look at the chemicals, the leftover A and B, as well as the AB gas, do they have higher internal energy or lower internal energy than they started? We're kind of split here, okay? So what would be your reasoning? I agree with the work is done by the reaction on the air. So is energy flowing out of our system or into our system? Remember, I said energy, not heat. We haven't figured that out. Yeah, it's leaving it. So energy is leaving the system. So we're over here in this case. And so we know that energy is never created or destroyed, it's just transferred. If we're transferring energy out as work, that means the internal energy of the system is going down. Now, is this reaction endothermic or exothermic? It's very likely to be exothermic, but how would we be able to tell for sure? That's right. We'd have to calculate the delta H. And that's what today is all going to be about, is calculating what the enthalpy change is. Because the enthalpy change isn't necessarily indicative of the work that's done. Because if we look at delta U here, and we know that our work term here is going to be negative, so we're going to have Q plus work. Well, if work is negative, then the size of Q is going to determine what's going to happen to our internal energy. And so we need to know about the energy flow. So the delta U refers to the change in internal energy of the system. And there are a couple different things that go into that, and that's where we'll be heading in the next few days. So at this point, I want to kind of differentiate between some of the terms that we've been using. And so to do that, we're going to talk about a state function versus a path function. And these are pretty much exactly what you would expect. A state function has a value that is path independent. So in other words, as in the picture example, we would look at this as being change in gravitational potential energy. Well, it would be from the base to the summit, no matter what. It doesn't matter how you go about doing it. And so if we look at this, we have two different paths illustrated here. But both of them start at the same position and end at the same position. And so that's a very important thing for chemical reactions. This would be an example of like a catalyzed reaction versus an uncatalyzed reaction. The starting point and the ending point are the same, no matter how you get there. And so that change is going to be independent of the series of reactions that you go through. And that's kind of what we're setting up for Hess law, because when we add chemical equations together, it doesn't matter which order that we add them in together, and it doesn't matter if we use slightly different reactions when we're just doing paper calculations, as long as we start with the reactants we want and we end with the products we want. And so we'll be doing some examples of that today. Now, path-dependent functions. And in the case of like a catalyzed reaction, they can speed up the process, they can lower the activation energy, but they can't change the difference in enthalpy or internal energy or any of those for a given reaction. So heat and work are two things that it could really can really vary. Because like if we want to, let's say, we want to lift a book from here to here, we could simply go like that. Or, so that'd be option A. Or option B, we could lift it to here, then we could drop down to here, lift it to here, and then drop it down to here. The point being, the change is the same in each of these. And enthalpy is a state function, and we can see how we can get it to be a state function because we make some assumptions about the conditions that we're running the chemical reactions under. And the big assumption is that we assume that pressure doesn't change. And this is a pretty good assumption because most of the chemical reactions we do are done just with regular atmospheric conditions. And so, for the most part, the reactions that we're interested in are ones that occur under 1 atmosphere of pressure if we're at sea level. And so, when that's the case, and I'm not going to ask you to memorize the derivation, but it means that if pressure is constant, when we measure the heat change or the heat transfer by a reaction, we're actually measuring the enthalpy change. So even though regular heat is a path function, when pressure is constant, it's the same as enthalpy. So in our example here, what I'd like you to do is to calculate these two things. On the first one, we're talking about butane undergoing combustion. It says that it releases this much heat and does this amount of work. So what I'd like you to do, and report in the chat, is calculate both the change in enthalpy and the change in internal energy for this system. So just go ahead and input your responses into the chat. And some things that might help a little bit are up here. Okay, let's go ahead and try that. So delta U is going to be equal to Q transferred at constant pressure, that's what the subscript P means, plus the work performed. So in this case, how much heat was transferred? Yes, I think you have the right idea, Mackenzie. We just have a typo there. There we go. So 2658 kilojoules. So Shayna, QP is the heat transferred at constant pressure. So in a more advanced class, we would investigate something called QV as well. And that would be heat transferred at constant volume. And that gives you a little bit different measure of your energy that's being transferred. Okay, so we've got our Q, and we say that it does 3 kilojoules of work. We also said that it releases 2,658 kilojoules. So how should we indicate that that heat is being released to the environment? Hey, very good, Jonathan. Okay, there's a negative. And now we had to add work into it. So the question is that a -3 or is that a +3? Okay, it's written as a positive. The system is doing work on the surroundings. So does that mean that's a negative value for energy change or a positive value for energy change? We can scroll up and take a look. So some of that energy is being transferred out of the system. And so that's going to be a -3 kilojoules, for a total of -2661 kilojoules in terms of the internal energy change. And then if we're just looking at enthalpy, enthalpy is simply going to be -2658 kilojoules. Sure. So in order for something to do work on something else, we have to transfer energy. So if I'm going to raise this mouse from here to here, because I'm doing work on the mouse. Okay, I'll get to yours, Mackenzie. So since I'm doing work on the mouse, I'm having to lose energy because I'm putting energy into increasing the gravitational potential energy of the mouse itself. And so that means the work I'm doing means that my internal energy is going down. And that's what we're indicating by the negative. The negative means that the energy is flowing out of the system. Just like the heat energy that means heat is leaving the system and moving into the surroundings. Okay, so Mackenzie, to your question, so how do we know delta H and delta U are equal? But they're not. They're not quite equal because they've got a little bit of difference between them right here, and that's the work. And so if you have a change in volume, so the only way you really get a change in volume that's substantial is when you produce a gas. And so if you don't have a gaseous product, then enthalpy and internal energy are essentially equal to each other. But if you have a gas that's produced, like when we burn butane, that's right, Caleb. And so when you're producing gases, you're going to have some expansion work done. It's going to push against the other gases to make room. Sure, if work was positive, that means that you would say something along the lines of the surroundings performed X many kilojoules of work on the system. And Alan, yes, P delta V is equal to work. Well, remember we're going to do, the pressure is going to be constant here. So that's why we have it in front. Oh, that's not what I wanted. It's in front of the delta. And so we allow pressure to be constant. And so that if there's any work done, it has to be expansion work. Or I guess contraction work if you have multiple gases reacting to form fewer gases. And so that is where the work part of it comes into it. There's other types of calculations that you can do, I alluded to earlier, where you have the pressure is variable and the volume is constant. And that gives you a little bit different calculation in terms of what happens to the internal energy. Are you doing okay out there? These are great questions. Delta H is enthalpy. You find it by measuring the heat transfer. That's the nutshell. All this series of derivation shows you that as long as you're doing it under conditions where the atmospheric pressure doesn't change, then enthalpy is the same as the heat transfer. Okay. There are a lot of symbols, and there's going to get even more. So here we go. So when we start talking about enthalpy change, we're using something called thermochemical equations. And you should have seen these in Chem 115, but you may not spend a whole lot of time on. A thermochemical equation basically tells you that there's a certain enthalpy change associated with a certain chemical reaction. And so we're going to take a look at these, and I want to illustrate a couple points in terms of how they relate to each other. And so we're going to start off with the two bullets first, and then we'll go ahead and answer the example question. So first bullet says, why do equation 1 and equation 2 have different values of the change in enthalpy? Okay, so if we look at this one and this one, the product's in a different state. Very good. So what has to happen for the product of 1 to match equation 2? Keep going along those lines, Ellen. There's got to be another step here. State of matter change, absolutely, Mackenzie. So what we would have to do is we would have to have a second equation where we take A2, B gas and condense it to the liquid. Because now when we add these together, what's going to cancel out? The liquids. And so that means whatever the delta H is for this second equation we just put in is actually the heat of condensation, just like from Chem 115. And so what would that value be? So if we add our blue equation to the one above it, what does that value have to be in order to get us to equation 2? Yeah. That's exactly what it needs to be. Does this make sense? When we go from a gas to a liquid, is it an exothermic process? Yeah, absolutely. Is this an exothermic process that we came up with? Absolutely. Now, a second aspect here. So we're starting at the negative 126, and we need to get to negative 186. So if you want to do it as an equation, you could do it like this. You could say negative 126 plus x equals negative 186. Because we're transforming the first equation into the second equation. Alrighty. The second thing I'd like to point out is, yep, that's Hess's law. We just did an example of Hess's law. We summed two equations together to get a third. Now, granted, this is an easy version, but it's still Hess's law. So let's take a look at our example problem now. So it says if 0.22 moles of A react with excess B to form A2B gas, what is the change in enthalpy? Now, we have some options here. We have A reacting with B to give our product as a gas in equation 1. We have A reacting with B to give our product as a gas in A as well as B. So which of these do we want to use? Or does it matter? It doesn't matter. Absolutely correct. What we're trying to figure out is how much is the enthalpy change if this amount of A reacts. And we want to convert that to a value of kilojoules. But if we use equation 1, that's going to be 2 moles of A react to release 126 kilojoules. But could we just as easily use equation A? Yeah, it's just double. And could we use equation B if we figured out what the delta H is? And what would be the delta H for that one? Right, Mackenzie. It doesn't matter as long as you use the correct coefficient and the correct enthalpy value. And so to finish this one off, how many sig figs should we have? Wouldn't the enthalpy be negative 252 for... Right, it would be, the enthalpy would all be doubled. So if we were doing A, instead of having this, we would have negative 252 kilojoules per 4 moles of A. But we're still going to get the same result overall. Yep, we used the top one for this one, but we wouldn't have to. We could use equation A, and I think in a future version of this, I'm going to have equation 3 and equation 4 in there instead of A and B. And so then what would be our missing change in enthalpy here? So B is change of H is negative 63. And then our final answer here, I guess if we used B, we would have to use negative 63 kilojoules over 1 mole of A, if we did that. And so our total answer here is going to be what? Regardless of what unit conversion we used. Okay, so let's compare everything to equation 1. When we take a look at equation 1, to go from here to here, we multiplied everything by 2. To go from here to here, we saw the same multiplication, which makes sense because if we're involving double the amount of reactants, we should get double the enthalpy change. When we went from here to here, we divided by 4. And so again, if we're using 1/4 of the reactants, we should have 1/4 of the energy change. Yeah, they're all the same ratio. And so the point of this was to illustrate that when we have to change the coefficients by a certain factor, we want to also change the enthalpy by the same factor. So that's kind of a key thing to Hess law. All right, so one thing we'll do now, this is more directly related to your lab, is we're going to start talking about kind of standard states. And technically, we're supposed to use 1 bar as pressure, but 1 bar is pretty close to 1 atmosphere, and chemists just kind of ignore that. The other thing is that enthalpy doesn't change very much in small amounts of pressure change. So what we're going to figure out here is something called standard enthalpy of combustion. Okay, so with combustion, there's a key indicator that we're dealing with a combustion reaction. And we're only going to work with organic combustion reactions. And so that in ours, it must react with O2. That's a clear indication that a combustion reaction is occurring. So let's go ahead and balance this chemical equation. And there is one caveat, is that we have to have only one molecule of ethanol. So we can't change this coefficient in front of ethanol. So here we go. 2 carbons on the left, 2 carbons on the right. 6 hydrogens on the left, 6 hydrogens on the right. How do we balance the oxygens? What coefficient do we need in front of the O2? I have a 4, a 3, a 2. Well, let's count up the oxygens. On the right-hand side, we have 7 oxygens. Over here, we have 1 here, so this has to provide 6. Yeah, that's right, okay, that's 6 plus 1. So we need 3. So for this one, it says, what is the enthalpy change for the combustion of 23 grams of ethanol? Okay, just a regular Stoich problem. We start off with 23 grams. And we're going to have to convert it to moles. And then we'll have to convert from moles to kilojoules. So, what is our molar mass that we need to use for ethanol? Okay, so 46.07. And then how do we set up the conversion factor at the right here, from kilojoules to moles of ethanol? Okay, negative 13668, very good, over 1. Right on. Okay, so if we go ahead and multiply this through and round off to the appropriate number of sig figs, what should our answer be? We have negative 680. Do I have a confirmation of that? Okay, so there we go. So, how do we know it's negative? From up here. And so that's why we have to look at all the material provided in the question, because it'll tell us if this is going to be exothermic or endothermic. All right. Now, we're getting into something that is on your lab. So standard enthalpy of formation. And so this is a little bit different, and we have to look up some data. It says 1 mole of compound forms from its elements under standard state conditions. Okay, so as we saw earlier, standard state refers to 1 bar or 1 atmosphere and 1 molar. So if we're going to calculate this for ethanol, we need to start off with carbon as a solid and as graphite, not carbon as diamond. Hydrogen, under standard conditions, is going to be a gas, and oxygen, under standard conditions, is going to be a gas as well. Graphite is the more stable form of carbon. Diamond is actually less stable than graphite, so over time all diamonds are going to turn into graphite. So what we'll then have to do, well, the quiz would tell you. So our next step then is to look up the delta H values for each of these. And so to do that, we're going to go to your textbook and go to Appendix G. So I'm going to change my share here. So let's go to OpenStax. Come on, let's share. Oh, Chrome is puking on me here. Yep, it's all locked up. Fantastic. Okay, can you still hear me? Okay, I'm back. Microsoft Edge is not my friend today. So, I'm going to go ahead and share my screen. We'll do it down here in screen 1. All right, so hopefully everybody can see that. So where you want to go to look up these values is on our textbook. Go down here to Standard Thermodynamic Properties. And we had to look up carbon as graphite. So we'll scan down here. Carbon as graphite. Well, that's 0. Okay. Well, let's go look up hydrogen. Hydrogen H2. Well, that's 0 too. And then finally, we're going to look up oxygen. And that's 0 as well. Well, let's go ahead and look up our see if we can find anything for our other one. But no, nothing. And so what we have is we have a case is that when we go to find out our delta H naught Fs, and I'll explain what each of these means. This means that we're doing it under standard state. The F means formation, so from its elements, we're going to have to go through and figure this out. So we need to find what our ethanol is going to be. So we have to go back to our table. Let's see if we can get there. CH3, OH, C2, H5, OH, And notice that there's a difference between liquid and gas, just like in the example we used before. So we have to figure out which one we're working with here. So we flip back, we're working with the liquid. So we come back to our appendix. We're working with the liquid, so that's negative 277.6. So this one was 0, that one was 0, and that one was 0. So our change overall is going to be the products minus the reactants. And so this would be negative 277.6 kilojoules minus all of the reactants added together. So that's going to be 0. And so the formation is going to be negative 277.6 kilojoules. Now, if we were going to set this up to actually make use of it, if we're going to form 2.5 moles of ethanol, it is, again, is just a straight up stoichiometry problem. So ETOH is our chemical shorthand for ethanol. For every 1 mole of ETOH that's going to be produced, we know that we're going to release 277.6 kilojoules of energy. And so what does that turn out to be after we've rounded it appropriately? So please go ahead and enter the value into the chat. ETOH is ethanol, so negative 690 kilojoules would be our answer here. Now, let's go ahead and take a look at how we use Hess law now. And so our specific, and this is a harder version of Hess law problem than we saw before. So as we said before, enthalpy is a state function, so we can add these in different orders, but the overall change is going to be the same. Got it, Abigail? Okay. So the overall change is going to be the same. So the first thing we have to do is get a balanced chemical equation here. So it says, calculate the standard enthalpy of reaction for carbon monoxide, CO, reacting with water plus H2O to form hydrogen and carbon dioxide. So H2 gas and CO2 gas. All right, when we balance this, what should our coefficients be? Now, we're not doing heat of formation, so it doesn't have to be just 1 as a coefficient. We just can balance it normally. Yeah, it's already good. So this is our target equation. This is the one we're going to try to form. These are our component equations. And so we're going to try to combine these equations in the box so that when we add them together, we get the one on top. And I'll just do this one fairly quickly, and you can ask questions in the chat. So I need to have a carbon monoxide on the left. It has to be a reactant. The carbon monoxide I see, however, is a product. So I'm going to flip it. Everybody good with why I changed the sign? Okay. All right. Again, we're trying to move along to our one. We see that we need to have water as reactant, but we've got water as product. So we need to flip that one as well. So we'll have 2H2O gas react to form 2H2 gas and O2 gas. And our delta H naught for this reaction is going to be positive 483.6 kilojoules. And now, at the end, we need to make sure that we have our products. Our products, H2 is on the product side. That's great. Exactly, Mackenzie. Because equations are endothermic in one direction and exothermic in the other direction. So if we flip it around, we have to flip the sign. So carbon monoxide's in the right spot, water's in the right spot, hydrogen's in the right spot, but we don't have carbon dioxide yet. So I need to have carbon dioxide on the products. In the third equation, it is on the products. So I can just use that one as it's written. I'll switch this over to save some space. So we've got CS plus O2G goes to CO2G. And this one doesn't flip because we're using it as written. So that part is kind of the straight up way to do this, to get things on the right sides. Now we have to make sure that when we add these up, we're only going to get the equation that we want up here at the top. So if we take a look at it, we want to make sure that we have only that nothing that doesn't appear in the final is showing up here. And so if we look through it, we've got some carbon here that doesn't belong there. We've got oxygen that doesn't belong in the final. And I think everything else, oh, there's some carbon here, some oxygen here that don't belong. And so we have to multiply an equation by a factor to get rid of things. And so what we see is that we have some carbon, and then we've got an O2 in the second equation. Yeah. So what can we do to the last equation to wipe it out? Yeah, Kayla. So we're going to multiply this by 2. So this is going to become 2 carbons and 2 O2s and 2 carbon dioxides. Well, that'll take care of the carbons. This 2O2 is going to take care of both of those oxygens. But also, remember that if we double the equation, we're using double the amounts. So we have to double the amount of enthalpy transferred too. So let's add these up. So when I sum this up, I'm going to get 2CO plus 2H2O reacts to form 2H2 gas plus 2CO2 gas. Okay, how was I able to cross out the top ones? Well, I'll use highlighter. This showed up in the products. It was canceled by this one, and this one were canceled by the 2 O2s. All right, so if we add it up, we're going to get a delta H naught for our reaction of, Abigail says, -7, 87 kilojoules. And we're close. Oh, thank you, Abigail. So let's go ahead and add this up then. So that'd be -787 kilojoules here. So when we add up our three changes in enthalpy, what value do we arrive at? Excellent. Think of 82.4 kilojoules. And that is not the correct answer. Exactly. And so, Haley, why do we have to divide by 2? The coefficients. Exactly. So in order to make our target equation, we have to take this whole thing divided by 2. What you do to one side, you do to the other. No, it's not because we multiplied by 2, because we just multiplied the third equation by 2. We have to divide by 2 because the equation we got, the green equation, is twice as big as our target equation. And so that'll take us to our final answer. We have arrived at our target equation. And absolutely, Haley, that's going to be -41.2 kilojoules. And so that's Hess' law, everybody. We are going to continue working on Hess' law tomorrow, and we'll do some more practice as well. Okay? Oh, it shouldn't have. That is an error on my part. Good catch, Mackenzie. All right, so 1 minute, and it's time to hop into the other one. So I'll go ahead and stop